Welcome Mechanics of Materials students. In this lecture we're going to be examining more mathematically the relationships between stress and strain for isotropic only materials in their elastic region where Hooke's law applies, and we're going to be examining relationships between our elastic constants, our elastic modulus, Poisson's ratio, and following from those we will examine and then derive relationships for our shear modulus and bulk modulus. So let's start with our simplest case, and that's a uniaxial tension or compression test. So we have a round cylinder that we've placed such that the cylinder axis is the y-axis, and the x-axis and z-axis are kind of pointing out in the radial direction. So if we apply some tensile stress, sigma yy, we can divide that by our elastic modulus and get our strain in the y direction. And then if we want strains in the x and z directions, we can apply the definition of Poisson's ratio and drop in our axial stress and then multiply by Poisson's ratio and put a negative sign. So our 1 over E times sigma yy is EYY. We've multiplied by negative Poisson's ratio, and that gives us sigma XX and sigma YY. Because we have an isotropic material, we have one elastic modulus and one Poisson's ratio, so EXX and EZZ, in this case, they're both radial strains, and because we're only applying stress in one direction, in the y direction, EXX and EZZ are the same. So this is a fairly simple version of Hooke's law where we have strain in all three orthogonal directions in terms of a couple of elastic constants and then the applied stress. Okay, obviously, what happens if we want to apply stress biaxially or even triaxially? Maybe we're going to push and pull on something in all three directions at once. We can take this same set of relationships where we say the normal strain due to stress applied in that same direction, so strain in the x due to stress in the x, strain in the y due to stress in the y, strain in the z due to stress in the z, is just going to be that 1 over E relationship, and then we can collect the strains in the other directions as being due to that Poisson effect and in the negative, but write it in terms of stresses and group some terms. So if we do a little mathematical wrangling of this relationship, just using the definition of Poisson's ratio and our linear relationship between stress and strain, we can apply those two concepts to stresses applied in three different directions. And again, we're still talking about normal stresses only. So far we don't see any taus, and we noticed all of the subscripts have the same axis notation for both subscripts. So we're only talking about normal stresses and normal strains at this point. Now, we are not in a state of hydrostatic compression or volumetric dilation, because the strains in all three directions aren't necessarily the same. So we could have some shape change, but we don't have any applied shear stress, and so we don't have any shear strain in each of the different directions. Okay, so I didn't go through the derivation of these three relationships, but it just literally does follow from the definition of, especially of Poisson's ratio. But we can just kind of take a look. We can see within each of these we have, if we FOIL and multiply out, we're going to end up with our first component just representing the effect of stress in the direction in which we're concerned with strain, and then if we multiply further, what we're seeing is effectively strains in the other two directions that would result from applied stresses in those directions. So basically, where we can have strain, for instance, in the z direction without necessarily applying any stress in the z direction. And in that case, it would be going in the opposite direction of the applied stresses in the other two. So that's something to watch for. So if we had a biaxial stress state, say where we applied positive stress in the x direction and the y direction, we didn't apply anything in the z direction, we'd get the material kind of stretching in the x and stretching in the y and then contracting in the z. So it would get bigger in area in the xy plane but thinner. So that would be the elastic change. Now we can get strains not just from applied stress but from a temperature change. So if we wanted to include the effect of temperature-induced elastic strain, we could add this term to the end of each one of these equations, plus alpha delta t to each one of these, plus alpha delta t. And alpha in this case is the linear coefficient of thermal expansion, and it's usually in degrees per degree Kelvin, and it's usually on the order of something times 10 to the minus 6, so it tends to be very, very small. But that is reasonable considering that we typically have strains in the microstrain range. So obviously if we have a temperature increase, alphas are positive, so if we increase our temperature, that's going to lead to a positive strain. So even if all three stresses, applied stresses, are 0, we can get an increase in strain, a positive strain, if we just heat the material up. And notice alpha, again, is the same in all three directions if we have an isotropic material. If we don't, it wouldn't necessarily be the same. We could have an alpha 1, 2, and 3 in that case. Which leads us to the assumption that we've been making so far. We now have kind of 3 elastic constants that we're looking at that we can use to calculate strain for a given stress and temperature change, or stress from a given measured strain and known temperature change. The fact that we only have 3 of them and we're considering 3 different directions means we have an isotropic material. If the material wasn't isotropic and properties varied in a different direction, we would have a different E, a different Poisson's ratio, and possibly a different alpha for each different direction where those properties might be different. And of course, so far, again, normal stresses only. Shear stress will have its own elastic constant. So it's coming up, don't worry. Speaking of which, let's take a look at shear. So the easiest way to look at shear is with a cylinder, because it's easy to envision torsion. So we're gonna take a cylinder, we're gonna twist it. So we're going to start with a right circular cylinder. So its center line is the z-axis. Our radial axis is in the radius of the cylinder, and so theta is kind of going around in the circumferential direction. So if we apply some torsion, torsional shear, we apply a torque to the outside of it, we'll get some shear strain. In this case, a gamma z theta or r theta, depending on which way we twist it. And so we'll get some deformation that is not normal. So we're not shrinking it and making the radius smaller, making it a skinnier cylinder. We're not stretching it along its axis. We're not spreading out the angle theta, which is related to r. Actually, all we're doing is shifting this around. So it is kind of important to realize when we're twisting and when we're stretching. So this is a pure twist. And in fact, a torsion test where you twist a cylindrical shaft or a ring is one of the easiest ways in material testing to make sure you're getting as pure a torsion, a pure twist as possible without unintentionally inducing any normal stresses. Okay, there's a little pause in the video because, as you can see, I've made a correction, which you'll see in the notes. There was an error in the subscript. This should have been a tau z theta, or z theta, and this is T for the torque. So we're applying a torque to twist the shaft, and it's being applied to the z face, not r face, and in the theta direction. So using our typical conventions for stress application: face first subscript, direction of application second subscript. So this is tau z theta, and it's going to lead to a shear strain z theta. So this is totally analogous to a normal force or a shear force in rectangular coordinates, say on the x face directed in the y direction, is going to result in a shear xy. So we're in that same system. So that needed correction on that one subscript. So having done that, we can say that our tau z theta on the z phase in the theta direction results in a shear strain, and that's engineering shear strain, z theta. And if we do a strain on the as an independent variable on the x-axis, and stress, shear stress, so a tau gamma instead of a sigma epsilon normal stress strain, we do shear, we'll see we get something that looks very similar. So we get a shear stress versus strain curve that starts with a linear elastic region, reaches a yield point, and then heals over. So this slope and this proportional elastic region for our shear stress strain curve is called the shear modulus, and it goes by capital letter G. So this is entirely analogous to our capital letter E elastic modulus. And in fact, we can relate it mathematically. In fact, we can relate all of our elastic constants, and the relationships are a little bit easier if the material is isotropic. In fact, quite a bit easier. But for the moment, we can make use of this particular relationship for each of our different orthogonal directions. So we can say that our shear stress in any direction is going to be equal to the shear modulus times the shear strain for that direction. And this is, again, engineering shear strain, not tensor shear. So, of course, remembering we have that 2-to-1 ratio. So if we want strain, we just have 1 over g times our tau. So xy goes to xy, xz goes to xc, etc. And of course, remembering with shear, because the stress and strain tensors are both symmetric, our xy is equal to our yx. So if you know one, you know the others. Okay. So we are not going to derive them, but we will just simply state that we can relate the elastic constants to one another. And as it turns out, our shear modulus is related to our elastic modulus and Poisson's ratio. So shear modulus will be the elastic modulus divided by 2 times 1 plus Poisson's. So that tells you right now, you know Poisson's ratio varies between 0 and 1/2. So shear modulus is always going to be a bit below, maybe about 1/2 to 1/3 of your tensile modulus. So somewhat less. We can step through the relationship between normal stress and strain and our volumetric strain, E, which is our change in volume divided by original volume. If you remember from our strain chapter, our volumetric strain is just the sum of the strains in each one of the orthogonal directions. And that could be with or without a shape change. But if you happen to be immersed in a fluid, and all of your stresses, therefore, in the normal directions are the same because you're immersed in a fluid, it's hydrostatic pressure. The same with differential, like if you went to high elevation. then you can relate that pressure to the volumetric strain again through Hooke's law. So in this case, each of those normal stresses is the same. We can relate each one of those stresses to strains via Hooke's law, because all the strains are the same, because it's related to the fluid pressure. It's the same on say, each face of a cube that's immersed. The strains are all going to be the same, so we can add them up and get this relationship for each one of the single direction strains. And of course our volumetric strain is going to be 3 of them, so we'll just end up with 3 up here. So our volumetric strain is just simply 3 times our strain, or excuse me, our stress in any one of our normal directions, provided they're all the same, divided by our elastic modulus times 1 minus 2 times the Poisson's ratio. And in this case we're saying that we're immersed in a fluid or whatever, so that stress is equal to the inverse of pressure, or excuse me, not inverse, it's negative pressure. Remembering our stress is default positive if it's tensile. So pressure is compressive, so sigma equals negative P. So we can get this relationship for the relationship between pressure, which is the same as negative normal stress, in every direction the same, and our volumetric strain. And if we group everything other than pressure together and turn it into one constant, arbitrarily we'll turn it into 1 over K, we can create another elastic constant called the bulk modulus. And of course we're going to stick it in the bottom so that it can cancel with pressure, and so our volumetric strain will be dimensionless. So K is the bulk modulus and relates volumetric strain, so dilation or bulk compression, with normal stress that is the same in every direction, otherwise known as pressure. And of course bulk modulus will have the same units as pressure and stress, which is pascals or psi. So to summarize, so far now we have 4 elastic constants that would apply if we have an isotropic material. So we have our tensile modulus or elastic modulus, sometimes known as Young's modulus, capital E, shear modulus, bulk modulus, and then the relationship between, and so these are all stress strain relationships. Then we have kind of a strain strain relationship in the form of Poisson's ratio, which relates axial to radial strain, presumably given the application of stress or maybe a temperature change. And remember that Poisson's ratio is going to vary between 0 and 1/2. And as it gets closer and closer to 1/2, the material is behaving more and more like an incompressible fluid, which it just so happens our bulk modulus ends up going to infinity, which is the definition of incompressibility. So we can look at that, in fact, scan back and look at this mathematically and show that this ends up being in the denominator for K, and so as V goes to 1/2, this goes to 0, we end up with a 0 in the denominator. So that a Poisson's ratio of 1/2 is defining effectively an incompressible fluid, and you will see that in practice mainly for elastomers, rubbers, things like that. Okay. If you want to use a shorthand, and I'll just go through this very briefly, but if you want to use a shorthand notation to write out all these long Hooke's law relationships, you can use the subscript or indicial kind of counter notation. I've got this just written out in my notes. I won't necessarily go over it. It will be useful if you start using this in programming or writing some matrix relationships to solve these, especially if you use these relationships for anisotropic materials. Anyway, so this is Hooke's law written with in indicial notation, where we have the I and the J representing X and Y, or R and theta. So this is written, or R theta or R and Z, whatever coordinate system we're in. And this delta ij is known as the Kronecker delta. It's defined as being 1 if your two subscripts are the same. It's defined as 0 if they're not the same. And that basically accomplishes what we need to make sure that we have a different definition when we do and don't have the same subscript. So if you follow this, you can basically replicate our former Hooke's law statements. Okay. Oh, and as last note, if you're going to use this, it's important to remember that this is tensor shear. So do not try to relate it to pi over 2 minus delta, which is for that geometrical relationship of engineering shear. You'll have to multiply it by 2. So now you know one of the reasons we've defined tensor shear, because it's a great way to drop into Hooke's law if we're going to apply some linear algebra to wrangle those Hooke's law expressions. Okay, the last thing we want to do is take a look at inverse Hooke's law, and this is just some mathematical wrangling. But what if you happen to have strain? Maybe you've measured strain. Strain tends to be much easier to measure than stress. In fact, it's used to measure stress. It's really not necessarily possible to measure stress. In practice, just about every kind of measurement having to do with mechanical properties is ultimately measured with strain and then related to stress. But we need to manipulate Hooke's law around a little bit to get expressions for stress in terms of strain. So again, I won't step through the algebra, but I have written some of these out, and you can basically substitute in for them. They're a little bit long, but again, they just involve, in this case, we have stress on one side and strain, modulus, Poisson's ratio, and then this last term will only be present if we have a temperature change. Remembering alpha is almost always given in Kelvin, so it'll be in some kind of number per degree Kelvin typically. Check and see which temperature unit it's expressed in. Okay. I warned you that anisotropic materials have a lot more constants, so basically you can have a different modulus and Poisson's ratio for every different combination of directions. So this just gives you an idea of what Hooke's law looks like if you indeed have a completely anisotropic material. So all of your elastic constants effectively have a different version for all three directions. You end up expanding things out quite a bit. So in that case, rather than writing EG and mu for Poisson's ratio, typically these first three are just lumped into a single constant S with indicial notation and used to create a big matrix. So if we were to write Hooke's law, we would end up with a column vector for strains, the 2 times the tensor strain being our engineering strain, and this is our collection of elastic constants. So this basically gives you all three of these. We would effectively end up with a full matrix for this. So we are not going to work with that in this class, but I just wanted you to see it and get an idea of it, understand kind of what's going on under the hood. If you work with a finite element package and you're working with anisotropic materials, you will very likely be manipulating equations like this. Not a big deal if you are working with matrix methods, doing this with a program. but be aware that you're gonna have to know that the material is or is not isotropic, and in what cases you can assume something has some degree of isotropy. Maybe things are the same in two directions. Quite often you'll get your radial direction's the same and axial will be different. So I won't go into that too much. Ways to simplify. Having complicated our life, now here's the simplification. Quite often you will be able to make an assumption of plane stress or plane strain. So I'm just going to end up, again, I'm just simply presenting equations. You'll have some chances in quizzes and homeworks to manipulate them. But if we take out a stress, say we're working in plane stress, so say you've got a thin piece of sheet metal and you're stretching it around, and you know how far you've stretched or how much force you're applying in two directions. You can't apply force in the third because it's a thin piece of metal, it'll bend, it's not going to support any stress. We're in plane stress. Hooke's law gets a little bit easier. You can certainly get strain in that third direction, but you can't get stress. And then when we go and invert Hooke's law, we have one fewer equation. And likewise with plane strain, if we don't have strain in the z direction, we're now the opposite situation. We're at the center of a big thick piece of metal or some material that is constrained. There's stress in all three directions, and there's one direction that's not gonna move at all. We get another simplification. We go down to these two main equations, and then we can relate these a lot easier. So again, just some algebraic manipulations. I would highly suggest you grab your Hooke's law expressions for isotropic materials and just maybe make a cheat card so you're not flipping back and forth in your book. Write them out. If you want to derive them, it certainly doesn't hurt. Know where they come from. Basically starting with that fundamental relationship between your tensile modulus and Poisson's ratio, and then leveraging out the simple strain as a function of stress, Hooke's law expressions. That would be something worth deriving and being able to replicate. The inverted ones, maybe just write down. Definitely you won't be working with anisotropic materials, but at least you're aware of how big the constants matrix gets. And then simply be able to understand how not to mix up plane stress and plane strain. Plane stress means you have stress in only two directions. Plane strain means you only have strain in two directions, and you will, guaranteed end up having the opposite in that third direction. Plane stress will result in you having strain in that unconstrained direction, and plane strain is achieved by having stress in all three directions. Otherwise, Hooke's law is just a matter of application. So getting some practice, using expressions, plugging in, seeing what you get, and of course making sure you keep track of signs. That's the last warning. Remembering that each one of these can have positive or negative. We can be in compression or tension. We can have positive or negative shear. So other than that, that's it for Hooke's law. A lot of math, but fairly straightforward. So we'll see you again to take a look at how this works as we vary our direction within a given material with these applied stresses.